All right. Hi, everybody. I'm Wesley. I use they, them pronouns. I work at Google writing a new networking stack in Rust for a new open source operating system. But this talk is my own and is not the opinion of my employer. So today, I'm going to talk a little bit about how fast packets move on the internet and about why answering questions is important. So about a year ago, I was talking to a friend, and they told me, if you're at MIT and you ping a machine that's in Berkeley, and you look at the ping time, that packet actually travels at about 80% of the speed of light. So I was like, OK, maybe this makes sense. I guess it's going through fiber-optic cable, right? Light is pretty fast, I guess. But also, I've used computers, right? Like, I know that computers are slow. So maybe this doesn't make sense. And so I decided to spend a little bit of time investigating and digging deeper into how fast packets actually travel. So the first thing I did is I'll just ping some machine and see how fast it is, right? And so we get all this garbage back. We can see 80 milliseconds, right? And so I'm in New York City. This server, I happen to know, is in LA. So that's about 4,000 kilometers times 2, right? Because we're going there and back again. And then we divide by 80 milliseconds, and we get 100,000 kilometers a second. I'm like, OK, I guess 100,000 kilometers a second seems pretty fast or something. And then I'm like, wait a second. The speed of light is 300,000 kilometers a second. So what is this garbage, right? We're only getting 1/3 of the speed of light. We can do better than this, right? Then I think about it a little bit more. I realize, 150 years ago, if you want to get a packet across America, the way to do that is Pony Express, right? So we're 22 million times faster than that is the good news. So I guess the internet's pretty OK. But I still wanted to figure out, where is this 200,000 kilometers a second going? All right, can we get that back? And so the first reason this is slower is 300,000 kilometers per second is the speed of light in a vacuum, right? But we're not traveling through a vacuum for most of it. So there's a few different mediums we're traveling through. The first one is Wi-Fi, right? So this is a 5 gigahertz signal going through the air. And then that goes to the router. The router talks to the modem over Ethernet. So this is copper wires. And then the long distance is done over fiber-optic cable. And so for any particular medium, it turns out you can figure out how fast light will travel in it, right? And like for the Wi-Fi and the fiber-optic cable, this is really light, right? It's fundamentally the same thing. By figuring out what the index of refraction of that material is, which you just go look up online. And so for Wi-Fi, the index of refraction is 1.0001 for air. And so the speed of light is basically unchanged, right? 300,000 kilometers a second. For Ethernet, slightly different. We get 192,000 kilometers a second. And then fiber optic cable, the index of refraction is 1.5. So we get about 200,000 kilometers a second. And when I thought about this, I was like, wait a second. It's interesting that Wi-Fi is faster than fiber optic cable, right? Like, I don't think of Wi-Fi as being fast. So there's a couple reasons why this is. So the first one is, like, we think of Wi-Fi as being slow because there's a lot of noise and interference, right? There's just like signals going everywhere in the air. And so you have to resend packets a lot. There's a lot of packet loss. And so it feels slow for that reason. And then also there's much lower throughput, right? You can send things faster, but you can send fewer things per second. And so this is why like high-frequency trading people will use microwave links between Chicago and New York, say, is because if you shave 5 milliseconds off that, apparently you make a lot of money. So this explains about 100,000 kilometers a second of what's going wrong. But what is that other 100,000 kilometers a second? So the next thing I thought was, well, maybe the packet isn't going directly from New York to Los Angeles. It's probably going other places in between. And so in order to explain this, I'll explain a little bit about how computers talk to each other. Right? So say we're the computer on the left. We want to talk to the computer on the right. And at a sort of low level, there's only really one networking API, which is you can talk to a computer that's on the same network as you. You can send it a packet. Right? The problem with this is most computers you want to talk to are not on the same network as you. So what you do is you send a message to a router. The router says, OK, I'll send this in the general direction I think that computer is. Right? So we're the computer on the left. We send a packet. This computer says, oh, I don't know where this really needs to go, but I have a general idea of the direction I should send it in. So it sends it to the next one, sends it to the next one. Eventually, the packet gets there. Everyone is happy. Right? And so it seems like a good system, but you might spot one flaw in this, which is, say, we're sending another packet. We send it to this router. We send it to this router. And then this router gets confused. Right? It's not sure where to send it. Accidentally sends it up here. This router is like, oh, I'll send this over here. And then our packet is like stuck in a circle. It's wandering the internet forever and never reaching its destination. So this seems pretty bad. We don't get our packet, but also all of these packets going in circles will clog up the internet. So there's a reason this doesn't happen, which is the people who invented the Internet Protocol thought about this, and every packet has a field called the time to live. And what this is it's a number that starts at some value, and then every time a router forwards it, it gets decremented. So you subtract 1. And when it hits 0, the router that would send it instead sends an error back to the original sender and stops trying to forward it. So this is how you prevent this issue. Anyways, that's a little bit of a digression, right? I want to figure out where my packet is traveling, so I know how far it's going, so I know how fast it's going, so I can know exactly how slow this is. And so there's a way you do that, right? There's a tool called Traceroute. Maybe you've used it. You can do Traceroute, and it prints a bunch more garbage to the screen. Right? So what this is it's saying there's 11 hops, and it prints out the address of each router. And so the way that this does this is, first, it sends out a packet with a TTL of 1, right? Our first router gets that, and it immediately sends it back, since it's been on the network for too long, right? And so we see the address that we received this error from, we print that out, and then we send a packet with a TTL of 2. And we keep on doing this until we've made a map of the entire network. And so I think it's really cool that this TTL field that wasn't even designed for this was used to make this super useful debugging tool. I mean, I'd used Traceroute a bunch before, but I didn't realize exactly how simple it was. You can do it in about 20 lines of Python, right? This is a working Traceroute implementation. The socket API is pretty verbose, but I can walk you through it. So we create some sockets. These are what you use to send packets. We set the TTL to 1 and make a variable to keep the current address in. And then as long as we haven't gotten to the computer we want to go to, we're just going to loop. We set the TTL of the packet, and then we send it off to our address. And then we wait to get a response. And we'll get a response from the router. We'll record the address that we got and print it out to the screen. And if there's an error, we'll just print out a star so that we know there was an error, and then increment the TTL by 1. And so this is Traceroute, right? This is a working Traceroute implementation. I think it's really cool that such a useful debugging tool is like both a hack and so simple. But anyways, let's return to the output from this Traceroute, right? So usually when I send a packet, I don't think about where it's going, right? It's just, oh, the packet goes to the place and it comes back. So it's interesting to take a look at what's happening here. So first we see gateway.net.recurse.com. I was at the Recurse Center while I was doing this, and so this is the name of their router. So that's the first hop. The second one, though, it doesn't have a domain name associated with it. So I was like, uh-oh, what am I going to do with this? It turns out the organization that assigns IP addresses has a tool you can use to look them up. So I just plug that in. It's Stealth Communications, which is an ISP in New York. So figured that out. The next one is Cogent, a multinational ISP. This is only in New York, and then it gets sent to Telia for the long haul. Then I see these other addresses. I'm like, I know what to do with addresses now. I'll just paste them into this thing, and it'll tell me. Then I see these addresses are in use by many millions of independently operated networks. I'm like, OK, I guess this doesn't work as well as I thought it did. So it turns out that you can send a packet from any IP address you want, right? And so these routers are just not publicly routable. But we can take a look at the link beforehand. We see Encapsula IC, so Encapsula Interconnect. And what this means is Telia is sending it to Encapsula, which is a DDoS protection service. And then finally, it gets to the destination. And so I think it's really interesting to look at this, because I don't think about this when I'm going to a website, but we just went through 4 or 5 different companies, and there's a bunch of really complex geopolitics around this, like who will send their packets to who routes where. There are companies that bury fiber optic cable without even intending to use it, since they think that a market will emerge later and they'll be able to sell it to somebody else. So I think this is really fascinating, that there's all of this politics that you don't have to think about, because you just send a packet somewhere, you hand it off to a router, and it gets dealt with from there. But I want to answer questions about how fast are packets in general, right? I still don't really have an answer to that question. And this data sort of gives me a little bit more information, but it doesn't give me enough to answer general questions. So we'll need to look somewhere else. And it turns out, who cares about how fast packets are? Well, ISPs care about this a lot. And so some of the ISPs publish their data. Right? The first one that I found was AT&T. So this is their network latency chart. And it's worth noting this won't get you the full latency, right? Since you'll ignore some hops on the beginning and end, which are also likely to be some of the slower parts of it. But it'll give us an upper bound on the speed. So you can write a script to scrape this page, and then this is the speed that these are going at in kilometers per millisecond. This is sort of hard to read, so I was like, well, what analysis am I going to do on this? First thing is, let's just print out what the fastest and slowest links are. And this is a little bit interesting. The first thing I noticed is if you look at Denver, Colorado, it has both the fastest and the slowest links, right? So it doesn't look like speed is highly correlated to cities. And that's sort of true if you look at the data in general, right? Mostly links are fast or slow. Cities aren't particularly. But it's still sort of hard to get any real answers from data like this. So another thing I wondered was, are longer routes faster or slower in general? And I sort of expected them to be faster because more time is being spent on the fiber optic cable, which, 200,000 kilometers a second, it's not the speed of light in a vacuum, but it's still pretty good. Less time is on the ends where there's like buffering and like computers are thinking about things or whatever is going on. So I made a plot of this, and it turns out that this is generally true, right? There's a somewhat weak correlation there. I think this is mostly because there's lower variance on the long routes, and like people don't build really slow long routes. But it's also worth noting that because we're looking at data within the United States, even the really long routes are not actually that long, right? It's only about 3,000 kilometers for the longest one. But it's still interesting that this trend exists. So the next question that I wanted to answer was, how fast do packets move in general, right? Like, what's the average speed of a packet? And something that I've learned is whenever you ask yourself, what is the average something, the question you really want to answer is, what is the distribution, right? Since that's a far more interesting question. So what is the distribution of packets? So this is as a percentage of the speed of light in fiber. We can see that most of the routes are about 50% of the speed of light in fiber, but going up to like 75% or down to 30%. And it's like a skewed left distribution. So I think it's interesting sort of how much of this is in the like 40 to 60% range, right? It's remarkably constant how fast these routes are. So I spent about a week on this, and I was like, okay, why? What have I learned here? I don't care really about how fast my packets move, right? Like the answer is fast enough. And so I could tell myself, oh, I learned all of these things about how the internet works, about what the index of refraction means. I learned about how Traceroute works. I learned about the geopolitics of ISPs. I learned about all of these things. And the truth is, I'm probably not going to use most of these things either, right? I don't care about most of these things. So why do I think it was important to do this? And the reason is, I ask myself questions all the time, right? I see things, and I'm curious about them, and I want to know more. And most of the time, I don't have the time or energy or knowledge to go and dig in and figure out what is actually going on, what's really happening. But I think it's important to remind yourself that the world is fundamentally understandable, right? You can ask questions, and you can find answers to those questions. And so I think it's important to sometimes take the time to ask silly questions and find the answers to them so that you can remind yourself that the world is understandable. Thank you.